Hey, hello everyone. Welcome back to the AutoML seminar. I hope you all had a great start to the new year. Well, since there's obviously no better way to kick off the new year than by learning about linear recurrent neural networks, we have June and Ricardo here today to present their latest work on this topic. And June and Ricardo, they already gave a talk at the AutoML seminar some time ago about in-context learning of state space models. So I highly recommend to check out their talk if you haven't seen it yet. And yeah, with that, let me thank you and Ricardo for coming today, and please take it from here.
Okay, thanks a lot for the introduction, Aaron. Today I'm going to be presenting our latest work, which is called Unlocking State Tracking in Linear RNNs through Negative Eigenvalues. So this is a joint work with Julian Siems, Jörg Frank, Albert Zella, Frank Kutter, and Massimiliano Pontil. And so the talk is going to be divided in two parts. So the first part, I will first introduce what state tracking is. Then I will talk about linear RNNs and in general current known limitations of current architectures. And then I will speak about the theoretical contribution of this work, in particular the characterization of the limits of general linear RNNs, and in particular that positive eigenvalue don't allow for state tracking, and then how to unlock the state tracking abilities using negative eigenvalues. So this part is going to be, I think, roughly 30 minutes. And the second part is going to be like half the time, I think 15 minutes. And Julian is going to explain how to extend the range of eigenvalues of some architectures, which are Mamba and DeltaNet. And then he's going to be presenting synthetic experiments and language modeling experiments, and finally conclusions and future work. So I think there's going to be some time for question and answer at the end, but if you also have some questions during the talk, feel free to ask them. Okay, so let's start. So first, I want to introduce what state tracking is, because I think that is not super clear, and is kind of it can be a little bit elusive as a topic. So I want to bring like a real world example of this. So you can see in this GIF that this cat essentially is doing state tracking. So it needs to keep track of the position of the caps to understand where the ball finally is. And so in particular for this task, you have that the cat is shown the initial state of the system. So it shows where the ball is. Then the human does like a series of transitions, and finally the cat is asked, so essentially to recover the state of the system, to understand where is the ball. And the important parts of this problem is that the state is not observable, so the cat cannot see where the ball is, and so it needs to watch the entire sequence of the transition. So even if it skips just one, then it cannot recover the final state. So we can actually simplify and discretize this setup. So as you can see here, so in this discretization, what you have is three states, so which correspond to the position of the ball, and then the arrows correspond to the swaps of two caps. So in this case, as you can see, for some of the swaps, you don't change the position of the ball if it's not affected, so you stay in the same state, and for some other swaps, you are changing state. And what I just did was essentially to construct a finite state automaton, which is like one of the theoretical construction that we use in this work. So for finite state automaton, you need to have like four things. So one is the finite set of states, in which in the case of the cat is the ball position. They correspond to the ball position. Then you have a finite alphabet, which correspond to, in this case, the transitions that are applied to the state. In this case, the swaps. So you have three transitions. And then you have an initial state, which is the starting position of the ball, and a transition function, which tells you how to go from one state to the next when you see a given transition. And so in general, you can have even more complex finite state automaton, and state tracking is essentially the problem of trying to mimic a finite state automaton with a machine learning model. So in particular, trying the problem that we are facing is to try to map the sequence of transitions of the automaton, which are input to the model, to the sequence of states of the automaton, which are going to be the output of our model. So essentially you don't, so the model doesn't see the state, but it needs to recover it only from the inputs. But what about language modeling tasks? So for example, in text, where does state track occur in text data? For example, here we consider a problem where we want to track the state of a chessboard. And in this case, the input to the model will be a series of moves, and these moves are encoded in a certain way, which is you just give the start and then position of each piece. So in this way, the model does not have access at any time to the state of the system, but it needs to recover it essentially from the moves. Other situations which are maybe more interesting for real-world applications are, for example, code evaluations. So in this case, you are essentially presented with a piece of code where, for example, you have some change of variables. In this case, you are swapping two variables. And as you can see, when you read this line of the swaps, you don't know what is the value of the state. Okay, so you need to, essentially, if you do a series of swaps, you would need to keep track. Like the model needs to keep track of the state of the system to be able to then recover the values of these variables. Another situation is instead entity tracking. So this is more like a natural language example. So in this case, you have three people like Alice, Bob, and Carl. And then you state that Carl, so they each have a coin and Carl is the only one having a penny. So now, so essentially you set up the initial state like this, and then you might have, so in this case, it's only presented one trades between two people. You might be presented with a series of trades, and even here, like you need to do state tracking to essentially keep track of where the penny is. To end this part of the talk, I want to like present like cases where you don't have instead state tracking. So like, of course, if the state is observable, for example, in the right GIF, you can see that of course, like you don't need to do any state tracking. Like in the text case, this might be a bit more elusive to understand this because, for example, here on the left is the example that you saw before, while on the right you have this like a similar example, but you state that Carl is trading actually a penny with Alice. So you're actually revealing the state in that line essentially, where before you didn't. And so this makes it much easier, of course, to solve the problem. But of course, like in real, like in text data, it can be quite hard to understand where state tracking is actually needed. Okay, so now I will talk about what kind of architecture we are considering here. So we are mostly considering architecture that are used for language modelings and language modeling applications. So you have, of course, the transformer model. So in this case, the text is first tokenized, then is passed through an embedding layer, and then you have a series of like the forward pass of the model consists in a series of layers, and each layer has the same structure, which mixes essentially two things. So one part is called like usually is referred to as channel mixing part, where each token is considered independently. So you apply essentially the same transformation to each token, which is an MLP in this case. And then the second part is a token mixing part, where in this case is the multi-head attention, where you are essentially you don't mix information between the channels of your token vectors, which are in RD, but instead you mix only across the sequence of tokens. So you mix information across the sequence of tokens. And several alternatives have been presented to the transformer architecture. And for example, this is like a schematic of the Mamba 2 architecture. And also here you have a similar situation with the token mixing and channel mixing part. Although it's a bit intertwined in the Mamba 2, but the token mixing part is still separate. Let's say you don't mix tokens and channel at the same time. And an important characteristic of both of these architecture is that the token mixing part is parallelizable across the sequence length. And this makes it essentially efficient to run over potentially long sequences. And for these alternatives that we are considering here, this will be in the class of linear RNNs, which essentially can be computed more efficiently for long sequences than transformers. And like in the previous talk that I did at this seminar, I explained this more in detail. Okay, so let's formalize a little bit what we just saw. So I will talk about this class of models, which is called the linear RNNs. So they have a series of layers, as we saw before, and each layer essentially has two parts. So for the first part, what we do is we compute a recurrence, which is linear so we compute a state matrix. And to do it, we compute a recurrence which is linear in the previous hidden state. And as you can see, the two matrices A and B are dependent on the input token. And the matrix A, we call it state transition matrix. So then the second part, what we do is we compute the output, and we do it from like using the current hidden state and the current token. So here, for this part, in this function deck, what we might have is like either a normalization, or, for example, we could also have an MLP part. So the MLP part and the channel mixing part is in the decoder in this formulation. So several architecture like belong to this class of linear RNNs. For example, these two architectures, so Mamba and GLA, have the characteristic that the state transition matrix is diagonal. And this, of course, makes it much more efficient to compute. However, a recent architecture was proposed, like in this paper by Yang et al. And this was presented at the NeurIPS this year. And here you have that the state transition matrix A is actually, it can do both token and channel mixing, because it's not diagonal, and it actually has this other structure, which is identity minus a parameter beta, which is a scalar, times a vector outer products. So this KT transpose is a vector outer product. So the main takeaway from this slide is that to have this architecture, like to be able to run this architecture efficiently, what you need is both the linearity, so you need the state update to be linear in the previous hidden state, and heavily structured matrices, so either diagonal or identity plus minus vector outer product. In this way, you can parallelize it efficiently, and this method has been seen to be like quite competitive to transformer models. Moreover, you can also say that transformers are linear RNNs, but with a catch. So the catch is that the state matrix is infinite dimensional. So one of the dimensions of this matrix is infinity, and the A matrix is the identity. So it's quite a simple form of the state transition matrix for the transformer. Of course, since the state is infinite dimensional for the transformers, you cannot compute this recurrence. So you would need to use another thing. And this means also that it's less efficient to compute it for long sequences. Okay, so now I will talk about one of the simplest state tracking tasks, which is be able to track the state of the parity automaton. So this automaton corresponds to the games with two caps in the cat GIF that you saw before, and also to addition modulo 2. So in this automaton, you have two states, and essentially what you do is you stay in the same state once you see a 0, and you change state once you see a 1. So in this case, I animate it a little bit. So what you have is, so in this case, you start from the state 1, you are seeing a 1, so you change state. Then you see a 1 again, so you change state and you go to the state 0. Then you see a 0 2 times, so you always stay in the same state. And finally, you see a 1, so you go in the same state, and at the end, you see a 0, and so you stay in the same state, which is 1. So in the end, you get this input and output sequences. And so the goal of the model is essentially to emulate this automaton. So by reading the input, you should be able to compute this series of states as output. And what we are also concerned with is that we want to be able to handle arbitrary long sequences. So this is important if you want to do length generalization. And actually, if you fix fix the sequence length, the problem becomes somewhat easier. So this is what we would like to do. Of course, like if you run this finite state automaton, you will be able naturally to handle long sequences, but for transformers and other models, this is not the case. So of course you can have more complicated examples of automaton. For example, this is addition modulo 3, which is also, so addition modulo n will also be a subject of our theoretical contributions. And in this case, you add one additional state and an additional transition. You can see it's more complicated, but essentially it works in the same way as before. Okay, so now I will talk, I will try to give some intuitions on why parity can be problematic to compute if you don't have, if you don't allow for negative values in your state transition matrix. And to do so, I will basically simplify a little bit here. So this model, as you can see, it's a scalar linear RNN where the B function now is the identity, and the state transition matrix A is just a scalar now. And so you have two ways of computing parity. So one, since we have this equivalence between parity and addition modulo 2, one way is to simply set the state transition matrix equal to 1 for every input. And this is equivalent to just summing all the previous values in the state and then computing the modulo 2 function. Okay, so this is like you can easily see because parity is essentially computing addition modulo 2. However, if you do this, then the state can blow up. So if you have that the inputs are always 1, for example, xi is equal to 1 for every I, then the state ht can grow with t, and so it can blow up for arbitrary. Like after a certain point, you will not be able to represent it, for example, in finite precision. However, you have a much more elegant solution, which is that you simply put the state transition matrix equal to -1 each time you see a 1. And in this case, you can easily check that this recursion will give you parity already in the hidden state. So the hidden state is already like a binary value, so either 0 or 1, which is the parity of the sequence. And of course, this means that the state does not blow up anymore, but you need to use negative values for this. And why is this a problem? So this is a problem because current architecture, so if you write down the parametrization of all the modern architectures, you can see that all the state transition matrices have positive eigenvalues, which are also bounded like in 0, 1. And so actually I didn't say, but these linear RNNs are quite general. So I only put 3 models here, but you can actually have many more. For example, mLSTM, which is one instance of XLSTM, and other methods can be framed like this, also linear attention. And this is problematic because, like, essentially what I told you before can be proven more formally. So for diagonal linear RNNs, if you have only positive values in the state transition matrix, you cannot solve parity. This was shown in a recent work at this NeoRIPS. Moreover, what happens is that you can prove similar things also for transformers. So even transformers can be shown not to be able to solve parity. And if you allow for an even like, so the main assumption that we use here is finite precision. So you use a finite set of numbers to represent your state, for example. And if you allow this set of numbers to grow with the sequence length, in this case, they allow it to grow logarithmically, then you can solve parity. But you cannot solve more complex problems which are related to state tracking. So you have like serious limitation both for transformers and diagonal linear RNNs in both these limited precision setups. In contrast, for RNNs and also linear RNNs with full state transition matrices, so where the matrix is not structured, then it's very easy and natural to be able to do state tracking. But of course, and they can do it also with one layer. So it's very, they are meant essentially to be able to do this, but they cannot be parallelized efficiently. So you have this kind of trade-off. However, what about recent alternatives, for example, like DeltaNet, which are non-diagonal, and but they can still be parallelized efficiently. So current result, they don't cover this architecture. And so in our contribution, we extend essentially this results for diagonal linear RNNs to non-diagonal ones. And what we show is that if your linear RNNs allow only positive eigenvalues, then you cannot solve parity. And this means that also DeltaNet with the current parameterization cannot solve parity. And secondly, we show that for modular counting, which is a subset of modular addition, so for example, addition modulo 3 is covered by this theorem, then linear RNNs must allow complex eigenvalues to be able to solve it. So if you only have in all of your layers that the products of the state transition matrices have only real eigenvalues, then you cannot solve this problem. And as you can see here, it might sound a bit convoluted, but this is so essentially it tells, like this theorem tells you that the numbers of elements in the product depend on the layer count. So if you essentially if you allow more layers, you can have more expressive models. So these two theorems tell you two things. So one is that current linear RNNs cannot solve parity because they only allow for positive eigenvalues, and that diagonal and also triangular, for example, real-valued linear RNNs cannot do modular counting. Okay, so if you only restrict to the diagonal, you are very limited in expressivity. Okay, so I want to give some intuition for the proof ideas behind this theorem, and also a little bit of a proof sketch. I think I still have some time for this. So, but first of all, like, do you have any questions up until now? Okay, so I will continue. So essentially, the proof idea for theorem 1 is the same as for the diagonal case, which was done in Sarrof et al. So when you you first present the model with a constant input, so you have that your sequence of inputs transition is just a sequence of 1. So then, in this case, the linear RNN output in finite precision will become constant, like you can show this. And the state, while of course the state of the parity automaton alternates between the 0 and 1. So here I just reported the parity automaton where I removed the transition for 0. So essentially what you do here, you can easily see that you need to alternate between two values while the output of the linear RNN is constant. So this is why current models, they cannot solve it. And so I will dive now a little bit more into the details of this. So the first step is to essentially, so if you have a constant input, you can see that for the case of one layer, what you have is that your recurrence is a linear time invariant, so it doesn't change across time. So this means that when you unroll it, you have this expression which involves the powers of the matrix A1 in this case. So this is a summation of all the powers. And then what we do is we set up the finite precision assumption. So what we assume here is a bit of a simplification. So we say that we have this function cast that goes from the reals to a finite set of reals which represent, for example, the floating point numbers, but could be in general any set. And this cast function operates in this way. So you project each numbers to the set D by essentially taking the closest one. And so you can see on the right that the cast function is essentially piecewise constant and has bounded range. And then we extend this cast function to matrices by applying, and also to complex valued matrices if you apply it separately to the real and imaginary part of each element of the matrix. So if before I told you about the state in infinite precision looks like this, then the model that we use for the finite precision looks like this. So essentially what you do is you compute the matrix powers and the products in infinite precision. Then you use cast to bring them in finite precision. After that, you do this summation in infinite precision, and finally you do cast again. So this is somewhat a simplified model because, of course, we are not using the previous indent state, but we are considering to do this matrix multiplies and sums in infinite precision, but it was used by previous work, and essentially the analysis gets much more complicated if you don't use this model because it breaks otherwise the associativity of the matrix multiplies is broken. So then we consider that any matrix can be, so any matrix power can be written in this way using the Jordan canonical form, where you have like two matrices, P and P inverse, and then you have this matrix JK, which is block diagonal with each block having this form. So this is a bit overwhelming, but it's actually like you can see that each element is either 0 in the bottom left, or is a product between the binomial coefficient and the like an exponential function of the eigenvalues. Okay. And so essentially what we did is to write each element, so the real and imaginary part of each element of this matrix, which will be the input of cast, as this sum. So you have a sum with some coefficients of these products between binomial coefficients and matrix and these exponential functions. And as you can see, so essentially what happens here is that since the eigenvalue, so what we would like is for each element AK, so for each AK to converge nicely, so to either diverge or converge nicely to a given value. So what we don't want is for this to oscillate. And here you can see that essentially if you have complex eigenvalues, in general, the exponential function can rotate, or oscillate between two values. Instead, if you have only real and positive eigenvalues, what happens is that you either diverge or converge, and this means that after the cast operation, these values become constant in finite precision. In turn, this implies that the state become constant in finite precision, and also the output become constant because it's a function of like for any DEC that you might have, the state become constant and the input token are constant for this example. So to sum up, what happens in the end is that if you only have real positive eigenvalues, then if you are presented with a constant input, then after a while, the output of the linear RNN will be constant. And this means that since the parity output needs to oscillate, you definitely cannot match this output. And then you can proceed, like you can continue the proof over the number of layers, because this was just the case for one layer. And what you do is you simply do a simple inductive proof, because you can see that essentially for the second layer, you would have a similar situation as for the first after a while. So after a while, your input will be constant as for the first, so you can apply the same steps as before. Okay, instead for the case of modular addition, so if you allow real eigenvalues, what happens is that you can write the powers of the eigenvalues in this way. So you have the powers of the sign times the powers of the absolute value of each eigenvalues. And this means that it is not going to be just one sequence that becomes constant, but it is going to be two subsequences. So essentially the subsequence of even values and the subsequence of odd values are going to become constant after a while. And this means essentially that the state of your recurrence and the output are going to be alternating between two values. So in this case, you are a bit more expressive, but you don't escape the fact that you can only represent essentially these alternating two values. And so here, for example, addition modulo 3 cannot be modeled, because if you have only two values alternating, you cannot model the alternating three values that are characterized that characterize addition modulo 3 when you have the input which is all ones. So this is essentially theorem 2. What we just proved is theorem 2 for one layer. And multiple layer is not as easy as for the parity case, because you don't have a constant input for the second layer, but you have two alternating values. So this becomes a bit more cumbersome, and this is why you need the products of state transition matrices in that theorem, but it still can be done. Okay, so I finished the hard part with the proofs. So now I will present so essentially before we saw the limits of current architectures. So now I will describe these other class of matrices. So what we said before is that diagonal matrices are limited, so they can only do parity with negative eigenvalues. But what about other class of, like also triangular matrices? But what about other classes of matrices? So what we consider here is the following class, where you have products of generalized Hausdorff matrices. So each element of this product is has this form. So you have identity minus a parameter beta times a vector outer product. And this is very similar to DeltaNet, but DeltaNet, it only has one element of this product. And essentially by increasing k, so increasing the number of elements in the product, you increase both the computational complexity of the method, because the matrix is going to be harder to compute matrix vector products, but also you increase the expressivity of the method. So you have a sort of trade-off with this k, which is the number of elements in the product. And then we also have another parameter, which is omega, which tells you the eigenvalue range of the interesting eigenvalue of this matrix, of the matrix CI. Yeah, so essentially, as you can see for DeltaNet, omega is the interval 0, 1, so it doesn't allow for negative eigenvalues. And interestingly, we can see that for this class of matrices, we can include orthogonal matrices only if negative 1 belongs to omega. So only if we allow for negative 1 to be an eigenvalue. And this is equivalent to setting here beta I equal to 2. And in particular, what does this buy you is that if you include orthogonal matrices, you can represent with only one element of the product a swap between two elements, which is a permutation of two elements. So essentially, in the example of the cat, you can model like a swap between two cups. And if you have a product of two matrices, you can model a swap between three elements and so on. And what we are able to prove is that for finite precision linear RNNs with only one layer, but that allows state transition matrices to be in this set, which is the set of matrices which can be written as product of generalized also their matrices with eigenvalue that include negative 1. Then you can model any finite state automaton whose transitions are permutations of at most k elements. So you need k minus 1 matrices in the product to model at most like permutation of k elements. And moreover, if you allow multiple layers and if you allow the numbers of elements in the products to grow, then you can model any finite state automaton. You can mimic any finite state automaton. So these are more general result, but you need multiple layers. So the interesting thing about these two theorems is that, for example, for theorem 3, this tells you that you can easily modify DeltaNet to have a state transition matrices that include negative 1, but only have one element in the product, and they can model swap permutations. And this makes them much more expressive than transformer models and also current linear RNNs. So before passing the ball to Julian, I want to recap the theoretical contribution. So what we show was that for any linear RNN with state transition matrices having only positive real eigenvalues, you cannot solve parity. And then we showed that diagonal and triangular linear RNNs cannot solve modular counting, even if you allow for negative eigenvalues. Then for the positive results, what we show was that if you have instead in your state transition matrices products of generalized Hausdorff matrices with negative eigenvalue, then you can mimic any finite state automaton, and you can do it in only one layer if your transitions are only permutations. There is also a nice open question still, which is what can be done with only a single generalized Hausdorff matrix if you allow for multiple layers. So actually it was quite interesting like I was very surprised to find out that you can model addition modulo M with 2 layers if you only have one GH matrix. So this was surprising to me because for addition modulo M you need to do rotations, so essentially you need a product of two GH matrices, like with one layer, but actually allowing for multiple layer helps. And we don't know what is the limit of this model with a single GH matrix yet. Okay, I finished my part, so I can pass the ball to Julian.
All right. Yeah, thanks, Ricardo, and hello, everyone. I'll be I'll walk you through how the experimental part and what the actual benefits for are on the empirical side of the eigenvalue extension. So how do we actually implement the eigenvalue extension for Mamba and DeltaNet, which are the two models that we considered on our experiments? For Mamba, we need to scale the components of the diagonal state transition matrix by 2 and -1. And this, of course, looks very trivial, but for Mamba, we actually had to change the CUDA kernels. And the forward pass was really quite trivial, but the backward pass is a bit more complicated because the derivatives changed a little bit and the way that they optimized it. For DeltaNet, however, it's luckily very, very easy. We really only have to scale the right part here, so the vector outer product. And this really just points down to a one-liner in the DeltaNet code. But this is really thanks to the really great work from the Flash linear attention library here, which is written by Song and Yan and co-authors. So if you're interested in linear RNNs, definitely check out this library. They basically implemented all the state-of-the-art linear RNNs. All right, coming to our first set of experiments on the Chomsky hierarchy, which is inspired by experiments which are also shown in the LSTM paper. So first question that we of course need to answer: can we actually solve parity now using linear RNNs if we use the extended eigenvalue range? And luckily, this is true. So in this experiment, we trained on sequences of up to 32 bits, and then tested on sequences from 32 to 256 bits in length. And as you can see, with the extended eigenvalue range, we obtain perfect performance. So we perfectly perform length extrapolation. And to demonstrate this a bit more clearly, you can see a length extrapolation plot here on the bottom, where the x-axis is the sequence length. And as you can see, with the extended eigenvalue range, the accuracy remains at 1, regardless of the length of the bit sequence that we measured. For those results are for the test performance of in the range between 40 and 256. And as you can see, the transformer did very poorly here. mLSTM also did quite poorly, but it also only uses the positive eigenvalue range. So mLSTM is a linear RNN, and SLSTM is a nonlinear RNN, and they are much more expressive. And SLSTM was able to solve it perfectly. So Mamba and DeltaNet, as you can see here with the extended eigenvalue range, so the entries with -1, 1, perform perfectly on parity. And this comes really at no cost at training or inference, because we only really need to make this small modification that I just showed you. All right, coming to our second set of experiments in the Chomsky hierarchy, where we evaluated modular arithmetic expressions. So the first one is without brackets, and the other one is with brackets, where without brackets is significantly easier to solve. And we again in the same setting, so we look at sequences of up to 40, of length up to 40 during training, and then during evaluation between 40 and 256. And in this case, the picture is a bit more nuanced. As you can see, again, SLSTM as the nonlinear RNN dominates over mLSTM, the linear RNN, in this case, again, as a comparison. Mamba and DeltaNet both significantly improve with the extended eigenvalue range. And especially DeltaNet almost perfectly solves the task for modular arithmetic without brackets, and still makes some progress on modular arithmetic with brackets in this case. And just to finish up this section, here's again a length extrapolation performance diagram, where you can see that DeltaNet got very good performance here for the modular arithmetic without brackets. Coming to a second set of synthetic experiments on permutation groups, which is much more closely related to state tracking. So in this case, we looked at the S5 permutation group of 5 elements. And just to simplify things in this slide, I'll only show results that we have for when we restrict this group to only swaps. So an example of a swap is when we swap the first 2 elements of this sequence of 5 elements here. And as you can see, the first 2 elements are swapped. And we'll look at, again, the same setting as in the previous case, where we have swaps up to 30, where we have sequences of up to 30 swaps. And then we look at the length extrapolation performance to see whether we truly learn to learn the right automaton, or where we learned some kind of shortcut which transformers tend to do. So as you can see here, a DeltaNet with extended eigenvalue range in just a single layer actually learns to solve S5 with only swaps perfectly. So it's a bit difficult to see, but the line remains here at 100%. And without extended eigenvalue range, it does actually quite poorly. And Mamba, because of the much less expressive diagonal state transition matrix, which doesn't allow it to actually to model swaps, can't solve it even with the extended eigenvalue range, which you can see here. All right, so if we look at the much larger group of the full group of permutation, the full S5, so the full permutation group of 5 elements, which you can see another example here. Then the picture is slightly worse, where you can see that the models, all the models that we consider here, can't even learn anything, can't even learn to solve S5 up to the sequence link that they learned that they saw during training. The extended eigenvalue range still tends to help, but it doesn't allow it to solve this problem. However, the full matrix, the full matrix linear RNN, which can't really be parallelized very efficiently, it actually can learn this task very well. As Ricardo also mentioned in the theory section, full matrix linear RNN is really just much more expressive and is a bit more comparable in terms of its expressivity to nonlinear RNN. So how can we make some progress here? So what we can do is to use the idea that Ricardo laid out in terms of the products of householder matrices. So we'll use these to make the state transition matrix of DeltaNet, which is this householder matrix of I minus outer product, more expressive by having products of these. And in this particular case, we'll actually simulate the setting a little bit by duplicating tokens in the sequence. So instead of having to simulate a product of 2 householder matrices, we'll duplicate each token successively in order to not change the code in this case. So what we saw in this case is that if we use a DeltaNet with 5 layers in extended eigenvalue range, we can make really significant progress on this problem. So the more expressive state transition matrix really helped here. Coming to our last set of experiments, which is on language modeling, where we trained 2 different DeltaNet models, 340 million parameter model and the 1.3 billion parameter models, and we trained them on 100 billion tokens of fine web. And then we looked at the length extrapolation performance on state tracking and retrieval datasets. So on the state tracking datasets, where we looked at code parity and math hard, we found that we get a significant and consistent perplexity advantage when using the extended eigenvalue range, which also persisted through multiple retrainings and changing of the training pipeline. So this really was quite consistent. And for retrieval, we didn't really see any performance improvement, so the extended eigenvalue range from 0 to 1 to -1, really only seems to be affecting state tracking as we predicted also in the theory. And those are the results here for the 1.3 billion parameter model, where the perplexity is quite a bit lower for all the models, but we still see the same trend here. And also note that the extended eigenvalue range actually didn't lead to any kind of training instability for either Mamba or DeltaNet. So you really can just change it and usually get better performance. Because in Mamba, actually, we saw a slightly different picture here. With the extended eigenvalue range, we actually get a little worse performance. With the same training setup where we also train for 100 billion tokens, and this is really because Mamba doesn't benefit that much from the extended eigenvalue range because of its more restrictive state transition matrix, because it's restricted to be diagonal. All right, okay, coming to our conclusion. So what you should really take away from this talk is that when you change the range of the eigenvalues from 0 to 1 to -1 in a linear RNN, you really can expand the expressivity of a linear RNN in a surprisingly strong way, which allows it to do state tracking. You should also take away that DeltaNet, or more generally linear RNNs with non-diagonal state transition matrix, which allow you to do token and channel mixing at the same time, are really vastly superior in terms of their expressivity compared to Mamba. So these new models, which have been coming out since June, are there. There's really something on the horizon that's very interesting. like for example, also RWKV v7. And as future directions, there's some very interesting ideas to follow up. So it would be great to understand what the real world improvements in language modeling are, because we only really showed perplexity differences in length extrapolation, but we didn't show, like, for example, performance improvements on some established language modeling benchmarks. It would be great to understand how you can further increase the expressivity of a linear RNN by finding other kinds of structured state transition matrices, state transition matrices, which are more complex. And finally, it would be great to understand whether there's some kind of fundamental trade-off between associative recall, which is kind of what in context learning tends to be kind of based on, and then also state tracking, and whether, like, you can really have both in this case. So thanks a lot.